And at that time, when I keep trying to search the other possibility, other software, and then I found this software which is Design Expert software. At that time, still version 6, and now we have I think version 13. And I asked my supervisor to bought this to buy the software, and then he bought that software. At that time, it cost around 5,000 ringgit Malaysia, and nowadays you can get around 1,200 for 2 license for the software, because at that time we don't have this, we call it as academic license. Okay, and that is the story when I started to use Design Expert software, and from the year 2000 up to now. Okay. So now can start with TOE. So what is TOE? Or you can call it as experimental design. There are two definition. You can call it a definition. You can get it from the software itself, and also from the Montgomery book. So the first, I think the meaning from both of these definitions is almost the same. If you want to identify the factors, the significant factors that will affect your process or your product, or you want to make optimization or improvement for your product or for your process, then you have to do the DOE, design of experiment. Or you want to monitor or to observe the output variables or the response of your process or for your system. So you have to do this, you have to manipulate the input variables. Yeah, you have to conduct a test of series which you can manipulate the input variables in order to observe the changes at the output variables. So even though I'm going to focus more on the DOE, but as the beginning, I would like to share with you some introduction on the RSM. So what is RSM? It's a combination of mathematics and statistic techniques, and you can present your data or your result by using the empirical model, or we call it as mathematical model. Okay. So when you present your data or your result with this model, mathematical model, you have to be clear. It is not when we are talking about engineering process, modeling is one of the big or the most important part in some of our study. If you can model something, I think it's a very good study to be incorporated in your thesis. But when you are using RSM or optimization process, you have to be very clear the model that you have produced is actually a mathematical model or empirical model regarding to the optimization process. It's just a part of your statistical analysis for the process. Okay, because you want to understand the process behavior, the what is happening to your process or to your system, then you can proceed for further improvement. So by using RSM, you can estimate also the interaction or the quadratic effects, not only the main factor. The main factor, which is the factor that you have been chosen for your study, okay, or throughout your study. If you have 3 factors, for example, okay, I'm going to use this simple example all the time throughout this sharing session. For example, you have 3 factors in your study, which are temperature, pH, and time. So by using RSM, you not only can understand the process behavior by looking at the single parameter or the single factor as it is, but you are going to look at the factors even by looking at the interaction between the factors, or if you are using, or you can get the higher order model, you can also looks into the quadratic effects or higher order model effects. Okay. So why RSM? So why RSM? Or why DOE? Even though you can see here there are 8 purposes or 8 objectives, but overall the ultimate goal or the ultimate objective or the ultimate purpose for this RSM is the same. You want to improve your process, you want to optimize your process, you want to understand your process or your system, you want to get the most influential parameters or variables that affect your process. And by doing that, you can reduce your time, your cost, because by using RSM, you can reduce, by using the proper technique, of course, you can reduce a lot of time compared to conventional optimization process. And also by doing that, of course, eventually it will reduce the overall cost. Okay. So as a conclusion, RSM is a useful technique for us as a researcher, especially in our area, science and engineering. But you have to be you have to really understand the concept and the basic of the RSM in order to use any software. So when we are talking about software, there are, I think currently there are around 3 common softwares you can choose, whether you want to use a design expert software. So currently they have a version 6, version 13, but I'm still using the old one, version 6. And most of my students also still using that because we have the license, we bought it last time. So make sure you have a proper license if you want to use any software, and because you want to publish in a reputable journal, so you have to make sure you have the license. And also Statistica software. I'm sure they also have the very newer version. And the last one is Minitab. I haven't tried Minitab, but I've seen some journals, some researchers, they have been published in many journals. They also been used Minitab for their RSM process. But these 2 software, which are Design Expert and Statistica, the most common software that has been used. Okay. So by understand that concept, you have to remember that DOE or design of experiment is very important tool. Yeah, it's very important tool. Okay, very important tools to improve your research or to optimize your process, to understand the behavior of your process. But in order to do that, you really need to have a good foundation, a good basis on what is DOE, what is experimental design. As I mentioned just now, you can do it without the software. You can do it without you can do it without any references, because it's just optimization process. You can use DOE as the tools to make your life easier, okay, for the optimization process. And in order to to explain the validity of your result, you need to have a good knowledge on the statistic, or else you just how or else how do you want to present or to describe your process, whether it is valid or not based on the ANOVA. If you can't explain what is ANOVA in the first place, what are degree of freedom, and also the sum of square error, the F test, the probability test. So you have to get you have to make sure you have those knowledge. You have to refresh yourself with those statistical knowledge. Okay, and eventually you can use software, yeah, as a tool to get those information on the statistic to analyze your result, yeah, based on the DOE. So I think we finished the first part of the introduction and the objective and the goals of DOE and RSM. Now we can start with the definition. Okay, with the definition part. So as I mentioned in the beginning of my sharing session, this is more on the introduction. Before you can have your own optimization process, you really need to understand this knowledge or this information. So when you have problem or you want to discuss your result, it would be very much easier for you. Okay. So the first variables that you should know is factor. I think everyone knows what is factor. So factor is the variable that you have been chosen in the beginning of your study, the factors that you want to manipulate, you want to yeah, we can say is you want to manipulate in order to see the output, the behavior of the process. The variables that can be we call it as a independent variables. Okay, the example that I can give you, most of the example actually based on the fermentation process, because this is my area of research. So in the fermentation process, it's similar actually to the chemical engineering process. We have a reactor, yeah, the reactor, and also almost similar in bioprocess engineering, we have a bioreactor. So the factors almost similar, which are pH, temperature, time. So these three factors, for example, if we choose for our study, we call it as independent variable or the factors. So we have, if you want to conduct a study, any study, in the first place you have to do literature review. Okay, when you do literature review, I believe that you will find around maybe 10 factors that affect the process. 10 factors, for example, you have 10 factors. Then from the literature review, you have to do critical review, and then you will reduce the number of factors up to, for example, 3 or 5 or even 8. Sometimes you don't have any choice because you don't know which factors you want to fix it. The values for the factors you want to fix it for that experiment. Okay. Then what you should do, so you have to do the screening from the literature review in the first place. Okay, and then after the screening process, you can choose the factors that you need for the experimental screening process. So that factors is actually the factor that you have to proceed for your experimental process in DOE. So that factor we call as independent variables. So this factor can be qualitative or quantitative. So what does it mean? So the examples that I've given to you, which are pH, temperature, and times, these are quantitative factors. Okay. quantitative, or in RSM we call it as numerical factors. Numerical factors. So we also have qualitative factors. We call it as categorical factor. Okay, in RSM we call it as categorical factor. So the example of categorical factors such as type of solvent. So you have three types of solvent. You want to optimize which one is the best, and that would be the factor for your study, and we call it as categorical factor. So I hope you get this. What is factor? Okay, and the second variable is response. So we have the input variable just now, which is factors or independent variables. So we have response or or dependent variables. So this one we cannot. We only have to decide what are those responses that you want to analyze at the end of your experiments. Okay, you have to run your experiment with this, for example, three factors, and you can see what happened to the process at the end of your trial or run or your experiment based on the response that you have chosen. So the response could be yield, percent of the protein, percentage of the, what else? The biomass percentage. So I'm sorry because most of my example actually from my background, which is bioprocess. Okay. So I already I've given you three responses. So in this run or in this trial, I have to get the values or determine the values from these three responses. For example, yield, percentage of yield, percentage of the biomass, and also percentage of the protein, for example, protein content or total protein content. So you can have one response or more than one responses for your study. So these responses, we call it as dependent variables. Okay. So now, how about the other variables? As I mentioned just now, that maybe from your reading, from your literature review, so you have 10 factors. You think that these 10 factors really affect your process, but I only want to choose 3 factors to study. So you have to be very careful. You have to justify why only 3. How about the other 7? What are you going to do with these 7? Because in order to conduct any experiment, you still need to put the values of these 7 factors, for example. Okay? So these 7 factors, we can call it as background factors or background variables. So initially, it can be the variable can affect the process or your experiment, but you have chosen based on some judgment, based on some references, you have decided to make it fixed at certain values. Okay, so that would be the background variables. Because these factors because of the some limitation, for example, your what kind of example I can give it to you? For example, you have you only have the static reactor. You cannot study the storing condition. So even though the RPM is one of the most important factor for your study, but you have this limitation. You don't have other choice. You have to make it at 0 RPM. So you know that it will affect your study, and you have decided to make it fixed for that specific study. So this is, we call it as background variable. So in what can I say? You make it as 0 RPM. It's actually one of the variable. Okay. So next, I think the last one for the variable is lurking variable. So from your reading, from your initial review of your references, you think that you have all the potential factors for your study, but actually you still have some other factors. So this some other factors that we don't know, we call it as lurking variables. We don't know what is it. So it's affect your study, but we don't know what is it. Okay. So we finished that part. We finished that variables. So you have to know that we have 4 types of variables, but the most important variables that you should know are factors and response. Okay, factors and response. So now, when you want to conduct any experimental design experiments, you have to know these principles. Okay, you have to know these principles. For me, it's a must. Yeah. The first thing is randomization. When you put all your factors and responses in the software, straight away I can say it's software because impossible for us, right? Currently we have those tools, so impossible you want to make it manually, so you have to put everything in the software. So you put the factors and the responses in the software, and the software will suggest you based on the design that you have chosen. The software will suggest you the run or the numbers of trial that you should do. Okay, straight away I will give you some examples. Okay, the first example, I think if you want to conduct a 2-level factorial design, yeah, 2-level factorial design with 3 factors. So 2 power of 3, you will have 8 trials or 8 runs. We call it as runs, run or trial or experiments. In RSM, we call it as runs, runs or trial. Okay, you will have 8 runs. So the software will give you probably in order runs. From these 3 factors, you will have 8 runs, and then you have to randomize that runs. Yeah, you have to randomize that run. You have to run. You get you print out that the trial from the software, and then you have to go to the lab to run the experiment, of course. So which one you have to start first? So you have to, maybe you want to start with the trial number 5 first. Okay, you start with the trial number 5 until you get the result or the analysis or the responses. You have these 3 responses, for example. Then after you finish trial number 5 experiment, and then you put the values or the result or the analysis to the responses, to the particular responses. And then, so next, for the next trial, which one you should do? So maybe you want to continue with trial number 2. So that is randomization. Because we want to avoid bias, we want to make sure that the effect like the calibration, calibration of the equipment, human error, because the problems or the error that occur during our experimental work is not it's actually comes from so many factors, from the batch of the raw materials, from the maybe some experiment you have to conduct it by yourself, but some you have to send it to the lab. The different technicians also maybe have different skills. You run the experiment, but the analysis will be done by other people. And then the calibration, the calibration of the equipment, maybe the buffer that you produce or you prepare, it's not almost definitely it will slightly different from every time you prepare a different batch, different error. And also human factors, also one of the most I think influence your experiments values or data. human factors. Because as a human, when we're happy, sometimes we can produce a very good result. When we have some difficulties, not according to that specific experiment in our life, for example, it will change somehow it will affect your result from your study. Okay, so randomization is one of the procedure that can probably it can validates our result to avoid those bias. We try our best to improve or to get the best result. Okay, and the second principle is replication. Replication also, you have to really understand what is replication. So replication and repetition. Yeah? This is the two. I think in general in general we have this replication or repetition also. You can explain in the same I think the same meaning, but in RSM, when you replicate your work, it means that you replicate the whole set of experiments. If you have 2-level factorial design, 2 power of 3, you have 8 runs. So you have to do, if you replicate once, and you have to do, or you have to conduct 16 runs, the whole experiment. You replicate the whole experiment from 8, you will have 16 runs. For these 60 runs, also you need to randomize. Okay, you need to randomize when you run your experiment, and also you replicate your experiment. And of course, at the end of each runs, you have to do the analysis. So you triplicate your analysis for each of the run. That is repetition. In your thesis, you always mention that you use Excel to do the t-test, for example, to get the average of your analysis, right? So that is, you triplicate or you duplicate your analysis. That is specifically for one file, not the overall study. So the replication means here in RSM is to replicate everything. Yeah, not only the analysis but the whole experiment. Okay, the next principle is blocking. So blocking, if you use design expert software, there is one thing you need to add whether you want to use blocking or not. Okay, so blocking, in my case, I haven't used blocking much because it depends on our nature of work. For example, you have 30 runs, 30, you have 30 runs. In some study, you can run these 30 runs in one day. One day you can finish all the analysis. But because there would be some or slightly error if you have to run it in the next day, for example. So, but because of the limitation of the equipment, or you have to queue, you need to make it at 3 days, 3 different days. Okay, so you can put that blocking, for example, 3 blocks. So 3 blocks, so 10 runs. You can do the analysis in the first day. The second block, which is another 10 runs, the analysis, you can do it maybe next week when you get your turn to use the equipment, and another batch will be the last one in the third block. So the software will consider that they will consider that if there is some error or some background noise that caused because of these non-homogeneous experimental units. Okay. Some example, if you have to use 2 batch of raw material, because in order to conduct 30 runs, for example, you need 2 batch of raw material, even though it is from the same source, but somehow different batch would give you a different result. So you want to differentiate, you want to incorporate these two batch into one RSM experimental procedure. So you can put two blocks. You make it like two groups. One group at one raw material, one batch of the raw material, and another group would be the second batch of the raw material. Okay. But for my case, I just want to share with you for my case, I'm doing fermentation process. It's quite impossible for me. Maybe some experimental procedure you can use it, but for me, it's quite impossible. For example, during my time when I did my master study, I have 5 factors. I have 32 runs. You just imagine 32 runs. And one run, I need 1 week. 1 week to complete one run. Because in fermentation process, we need two days, at least 2 days to prepare the inoculum, to prepare the microbe, to prepare all the equipment or the tools. So 2 days for the inoculum, and when we run the experiment using bioreactor, it takes another 3 days. 3 days. If we have a problem, contamination, we have to repeat everything, and we will waste the whole week. So there is no block up to 32. The block, I think, up to 3, 4, 5. The maximum, I think, 5. I'm not sure about the current version of the software, but at that time, previously, I think up to 3 blocks. So it depends on you whether you want to use block or not, but it will help you if there is so much differences between the batch of the experiment. I hope you get it, what I mean here. So we have finished that principles of experiments. Now, this is the time for the factorial design. Okay. Not yet RSM. So people are quite confused when we are talking about RSM, about factorial design. Yeah, in principle, you can say it's almost similar, but it's actually not. Okay. It's quite different in certain areas. So factorial design is one of the method. Yeah, it's one of the method if you want to study the effects of 2 or more factors. You have 2 or more factors, and also is very good for screening process. It is for 2-level factorial design. Yeah, for 2-level factorial design, you can use this method for screening process. Okay, before I proceed, I'd like to share with you some of the experimental procedure when you want to conduct any optimization process. When I most of the time when in the Viva session, when I examine thesis, master's or PhD thesis, many students, of course, you have to do optimization process, and you use RSM, whether Box-Bangken, Taguchi method, Blackett-Bowman method, or any method in RSM or in factorial design. You only focus on that process or on that method. What is the outcome from that optimization process using that specific method? The optimization is actually starting from the beginning of the preliminary study. When you have decided to conduct optimization process, okay, you have to start from the very beginning, from the screening of the factors. What are those factors that will affect your process? It's not focused only that optimization process at the end of the optimization. It's from the beginning. So in this case, I just want to show with you, rather than straight away what is RSM, what is factorial design, but you don't know what is actually you need to know behind the process as a whole. So I believe that I would like to educate you more on this concept, because when you really understand this concept, you can just read any journal, regarding your area, you really understand what they did. Okay. So, for example, in this study, this is journals from my student just finished his PhD. Okay, and this journal just published early of this year, January 2021. So this is Q1 journal. Okay, in this journal, he did screening process and the optimization process. But this screening process also part of optimization process. Okay. So this screening process, when he did literature review, probably there are 10, like I mentioned just now, there are 10 or more than 10 factors will affect the process. So from that, maybe 10 or more factors, he think that this is only 8, right? These 8 factors would affect, but we cannot decide, yeah, we cannot decide which factors will affect most of the process. And because of so many things that you have to be considered, because you are using different type of process, sometimes different type of materials, so you cannot straight away decide it based on the readings, based on the references that you have, because you have to have your own novelty for your study, right? Especially for the PhD student. So many undecided factors. Then you choose to do screening process for these 8 factors. These 8 factors, okay. For the screening process, initial step in optimization, which is the screening process, you can choose whether you want to do conventionally, we call it as OFAC. I hope you already familiar with OFAC, one factor at a time method, yeah, OFAC. And also 2-level factorial design. These are the 2 most familiar process or method that you can use for your screening process. Why screening is very important? You cannot straight away go to RSM, go to do your optimization process to get the optimum condition when you have so many factors that you don't know which one is the most influential to the process. So you have to do screening. So this this particular study, he chose to use 2-level factorial design. Why we call it as 2-level factorial design? Because in 2-level factorial design, we have these 2 coded values, -1 and +1. This is the low value and the high value. That's why we call it as 2-level factorial design. To those who still not familiar, or in the very beginning of the study, maybe you don't know what is 2-level factorial design. We call it as 2-level because we only need to decide this 2-level. Okay, after you read your literature review, for example, you think that this is not think, must come with facts and figures. Why? This Lacaze concentration is one of the factor, of course. And how about the low and high value? You want to see within the range that you have been chosen from the literature review. This one also you have to decide. Yeah, the factors, the low and high value, the range. We call it as the range. So how do you want to know which one is the best range for that particular factors? So this is also from literature review. You have to have a complete, perfect literature review or critical review in your study before you decide which one is the best. So during your Viva, definitely if you did this, okay, okay, when you finally there is a annotating features. Okay. When you choose this factor, for example, Lakis, and from those many literatures that you have read, and you choose 0.2 as your low value and 1 as the high value. Okay, same goes to the other factors. So this is the crucial part of optimization, but not very crucial in screening. But in optimization, yes, it's the most important part is to get the perfect or the correct range for the study. Because at the end, the mathematical model that you have developed from the statistical analysis based on this range only, not the range that you haven't covered. Okay? You have to understand that one first. That's why range, the choices of the factors and also the selection of the range are two extremely important part in any screening and also optimization process. Please remember that all the time when you want to conduct screening or optimization process. Okay, so during your Viva, I forgot that one. During the Viva, when you have this will be in your chapter 3. Okay, you will have this in your chapter 3. You want to show to the readers, to the examiners that these are the factors and these are the ranges that have been chosen. And the examiners will ask you, how do you choose these factors? From where? What are those references? Or these factors. So you have, that's why I mentioned again that you must have a complete, comprehensive, critical review in your chapter 2. I always remind my students, I always, I also want to stress here that, to emphasize here that critical review is the best thing, is the most important thing that you have to do in your chapter 2. Chapter 2 is not about writing as a textbook. We don't want to see textbooks materials in chapter 2. We want to see critical review. Critical review, what have other people have done in that specific area, what are those factors involved, and what are those ranges that they have been used, and the yields, of course, the yield. Okay? What else? So this is for screening process. And actually, I only want to explain why I cannot move this. Why I cannot move this slide? Wang Zuke, are you? Because I approve the annotating in the slide, so I can't. Okay, thank you. So factor design, normally for screening process, I want to show you that this is the factors, the coded factors, the coded values, -1 and +1. And next, in screening process, our main objective is not the optimum value or the optimum response. Our main process for screening is to determine which factors are significant to the study. That is the ultimate goal for screening. Optimization, of course, we want to determine to get the best or to the optimum value or yields. But for screening, our ultimate goal is to determine from these 8 factors which are the most influential, the most significant to the process, and the one that not significant, we want to fix the value and leave it as background variables. So you still remember the one of the variables that I mentioned just now, which is background variables. So we can fix it as a background variable. So that is the objective for screening process. And when you do a 2-level factorial design, in the first place, the software will not suggest you the center point. because we only have two levels, -1 and +1. So there is no the third values. But if you want to add another set of experiments, for example, we have two levels with 3 factors. We have 2 power of 3, which is 8 run of experiments. If we want to run another set of experiment at the center point, we call it a center point, and we code it as 0. So the software will give you another runs. You need to repeat it. For me, as the rule of thumb, if you have 3 factors, maybe you can replicate your center point 3 times, or 2 times also enough. It's just for 8 runs, you add another 2 runs, so you will have total 10 runs. So from that 10 runs, the 2 runs from the center point. This is the center point. You don't have to put the values in the software because you only have to put the -1 and +1. So the 0 values will be generated from the software as the center point if you want to repeat or you want to run the center point. But for me, center point is very important because if there is a possibility of curvature, because this is a screening process, it's a linear equation, 2-level factorial design is linear equation, it's impossible for you to get a higher order model. If you want to see at the 3D response surface, it's only a planar straight line of your 3D surface. So it's a best way to see whether there is a curvature or not, a possible potential optimum point or not from that factors that you have chosen and from that ranges that you have chosen in the first place. Okay, so I encourage you to add center point. So this is 2-level factorial design. It's quite difficult actually to separate between each topics because it's really you can see that is in order to explain that points you need to relate with the other points. So even though this is the part that I need to explain to you, I can explain to you what is 2-level factorial design, but I already mentioned in previous slides because the examples and the flow of the studies actually involve this design. So why 2-level factorial design is a very easy, simple method to use because it's only involve 2 level, low and high. Okay, low and high. So the numbers of experiment will reduce tremendously. For example, yeah, you can see here, you have five factors. So for 5 factors, okay, you can calculate by yourself. If you have 5 factors for screening process, or you want to do straight away optimization process because all those 5 factors are extremely significant, you don't have to check whether it is significant or not. So you straight away you decide you have decided, okay, I want to run optimization. I don't want to run screening, or I want to run screening just from the literature review. Of course, you can do screening process from literature review. Yeah, nothing wrong with that. So you can calculate it. 2 power of 5. 2 is because of 2 level. Power of 5. You will have 32 runs. Okay, you only have 32 runs. If you want to run all 5 with 5 factors, and each of the factors probably have 10 points, 5 points. For example, you want to study temperature. You have 3 factors: temperature, pH, and time. For temperature, you have 10 points. You want to study at 50, 60, 70, up to 100 and something. So you have 10 points, for example. And for pH, you have maybe 6 points from pH 4 to pH 10, for example. And for time, you want to study 1 hour up to 10 hours. So you have 10 points. So you just imagine how many runs you need for that 3 factors with those points for each factors. But if you run 2-level factorial design with that 3 factors, you have 2 power of 3, only 8 runs. Just imagine, only 8 runs. That's why we say that we can keep our experimental numbers at a reasonable size. Okay? What else for this factorial design? Actually, so many things. Okay, so many things. I only highlighted something that I think is quite important, and maybe some from my experience that I've come across to my students or during the Viva session. Okay. So this is design matrix. When you have decided your factors, the number of factors, and then you can put in the software, and the software will suggest you. So this is for 2 power of 2 design. If you have 2 factors, so basically you will have 4 runs for number of experiment of 4 runs. So this is the coded variables. So when you have decided what are those, for example, you have x1 is time, x2 is temperature. So this -1 and +1, you have to choose, you have to decide based on your literature review, based on your preliminary study, what are those values. That's only the things that you need to do. So from this, again, I mentioned to you, I emphasize to you, the choices of this variable and the range, the -1 and +1, is extremely important. If you have chosen the wrong values here, and you will not get the valid results or the valid model later on when you analyze your result. Okay. So these are another examples for 2 power of 3 and 2 power of 4 matrix display. You can see here. So this is 2-level factorial design all about. And one more thing, in this 2-level factorial design, what we can say more interestingly, we can say that if we have huge number of experiments, still huge, 32 is, for our case, for my case, 32 run for fermentation process, which you need one week for 1 run, is still too big. It's too much. Yeah, it's too much in terms of time, in terms of cost. So it's too much. So if the process or the screening process is just to determine the significant effects of the factors, you can choose to run fractional factorial design. Instead of 2-level factorial design, we have another term, we call it as fractional, 2-level fractional factorial design. So for fractional factorial design, for design expert users, design expert software users, you can choose. You can choose, for example, 2 power of 5, you have 5 factors. You can have 2 power of 5 minus 1. So instead of 32 runs, you will have 2 power of 4, which is only 16 runs. Okay? So if you're using factorial design for your screening process, you can reduce a lot number of your experiments. That is another advantage of factorial design. Okay? But that one only for a screening process. We are talking about screening process because screening process, it depends on our goal, and there is another term, we call it as resolution. So later on, afterwards, I'm going to explain to you what is resolution, and this resolution were very much related to this 2-level factorial design. Yeah, fractional factorial design. whether you want, you can or not, you want to use fractional factorial design with your study. Okay. Okay, so it's already 10. I think the time is okay. Okay, the next part is regression analysis. In the definition of the RSM, I mentioned that it's a statistics and mathematics. So it involves regression analysis or mathematical model because it involves statistical analysis. Okay, so from the statistical analysis, definitely you can come out with the mathematical model. So when we are talking about regression analysis, it's only the relationship between the factors and also the response. I think it's a normal definition. It's not only for this RSM, but in any other process you have the Y, yeah, the Y. In this case, we call it as the response, the Y, and also we have the X, X1 or X2, X1 or Sj. It is the factors. Depends on how many factors you have in your study. So this is the polynomial models, and you want to feed your data into this model. At the end, you can produce the mathematical model, and we call it as the regression equation. So for factorial design, we're still talking about the factorial design, not yet RSM. Okay, for factorial design, if we have only two factors, In this case, we have x1, for example, x1 time x2. X2 is temperature. So this is the linear equation for our process. For example, y is yield. So B0 is the constant, B1 also the constant for the x1, and B2 is the constant for the x2. So this equation will be generated by the software. But you have to understand how to read it, how to discuss it, and how to present it. Okay, if during the Viva, the examiner asks you, can you please explain the equation that have been developed from the process? Of course, you have to know how to explain it. Even the values of the constant also you need to explain, because it will determine, it will show with which factors is the most significant or influence the most to the yield, for example, because we have the values here based on the constant. Instead of ANOVA table, okay, from ANOVA table also, from the p-value, from the f-test, definitely you can see whether the model terms are significant or not. But it also can be reflected in the equation, in the mathematical equation. So if you have the interaction effects in the equation, so just now we only talking about the single effect. We want to see only what is happening to this yield, to the y, if we have only single effect, x1 time x2 temperature. How about the interaction effect? That's why we have x1 and x2 here, b1, 2, the constant for the interaction effect. So you can read, you can see whether the term is significant or not from the ANOVA table, from the model term. And if you include this as part of your model, you can get it, or we can put it in the equation. If not, from the beginning you can exclude it, the interaction terms. If it is not significant, you can exclude it as a model term, and your equation will only have these two terms. This is a very basic example I can show you. When you have more than 2 factors, of course, it's quite complicated. And if you have when you have quadratic or polynomial equation, it's much more complicated. Yeah, but the basic concept is just the same. Yeah, the constant, and also these are the model term based on the factors, based on the interaction, based on the quadratic effect. If your model is cubic, and you will have the cubic also here, the cubic terms in the equation, and these all terms eventually were reflected the yield here. Okay. I think I finished the first part of the first part of the process of the factorial design. Now, how about the RSM? Let us see into response surface methodology, RSM as the second order model. Okay, second order model. So factorial design, just I think this one also I take sometimes to really understand. When we are talking about factorial design, two-level factorial design is actually linear equation. Definitely linear equation. You cannot get second order model or higher order model or polynomial equation by using two-level factorial design only. Okay, you have to remember that. But if you want to have higher model, if you want to get the optimum point, then you have to go for RSM. That's why two-level factorial design is for screening. I hope that I can see into your face, and you can tell me whether you really get it or not, or you really understand that, because actually it took some time for me to really understand that concept, because you have to go through a lot of experiences before you can really understand. You can see only by looking at the equation, you know what is happening to the process. Looking at the ANOVA, you know what is happening to the process. So we can see from the equation that, okay, you have the problem during the selection of the range. We can know that straight away from the statistical analysis actually. So if you want to if you want to conduct optimization process after you have done your screening process, yeah, by using a two-level factorial design, or we have other design rather than two-level factorial design. For example, Plackett-Berman. If you have heard that before, Plackett-Berman, that one also involve linear equation. It's impossible to get higher order or polynomial equation. So that's why the purpose of using factorial design and Plackett-Berman design is only for screening process. It's okay, it's possible if you want to do optimization, because from the software, you can also do the analysis for optimization. No problem. Okay, no problem with that. But if you want to follow the proper method, a proper DOE, then this is the way. You have to go step by step. And if you want to skip that, there must be some reason, and you really understand the reason behind that. Okay, behind any decision you have made, even though the chosen of the range, you must have really understand, and you have to have the reason behind any decision for this process. Okay. How about the higher order model? So this is another example from my student journals, for my student publication. So in your left hand side, in my left hand side, I'm not sure about yours. This is one of the equation from the screening process. You can see here, okay, the words here, the sentence here, the relationship between all factors toward the activity. Yeah, this is the activity, the yield, the Y. So the activity shown by this equation, so the fitness of the model, this is R squared. Later on, I'm going to show you. And explain, the response can be explained. The response is the yield. Okay, the response can be explained by the linear model. So as you can see here, there is no quadratic effects, no cubic effect, no higher order model here. It's only linear equation. So straight away, I can say that this is a two-level factorial design. But somehow, if you are doing RSM, also you can have this kind of linear equation, because that is the only model that can fit your data. But why is that happen? Because you have missed most important parts during your early stage of the selection of the factors, the early stage of the selection of the range. Again, I emphasize again, and at the end, towards the end, I am going to emphasize it again. The choices of the factors and the choices of range are extremely important. It will affect later on your result, your model, your ANOVA table. It will make your life easier. If not, when you finish everything, when you spend 3 months to do your optimization process, but you still struggling with the lower value of R squared, lower value of your problem with your lack of fit. So you want to avoid that. Make sure from the beginning, the screening process, the selection of the range, and the selection of factors are perfect. Okay? So that means your literature review must be perfect. Okay? And the second example is the polynomial model. Okay, you can see here, we have a quadratic term here, quadratic terms as well as the quadratic term interaction. It could be a longer equation if you have many factors, right? If you have many factors, if you have many interactions, okay. Just I want to show you here, because we have limited time, we don't have opportunity to do hands-on, because in order to do hands-on, we also need to have the software, and also you have to need to have the module, because I actually have the module because I've conducted a series of workshop, and I'm going to during the workshop I give you from the very beginning, or from the simple example up to the higher model process. So as you can see here, there are three. Yeah, you can see here 3 factors: x1, x2, and x3. So you can see here there are 3 factors, single factors: x1, x2, x3, and also you can see here quadratic effect for x1, quadratic effect for x2, quadratic effect for x3, and then the interaction effect as a single factor: x1, x2, x1, x3, x2, x3. So next is x1 power of 2, x3, and also x1, x2 power of 3, and power of 2. Okay. So this is how you can read the model. And these terms, when we put into the equation, yeah, when we put these terms into this equation, please make sure all the terms are significant. Okay, you choose that. You can choose that from the ANOVA. So from the ANOVA table, you will have the p-value for each terms. So which one is the most important? Which one is not? Which one? Which factors or which terms? The significant terms will be incorporated into the model. Then the one which are not significant, you will remove it. You will exclude it from the model. So you cannot see here because you don't want to put as a model. So when you finish this, you have finished your experimental procedures, you finish all the trials or the runs, and then you put all the data into the software and you want to do the analysis. The first thing you need to do is to check whether your model is okay or not, your model is adequate or not, your model is valid or not. This is a very, I think for those who have this kind of experience, this is the most important thing, the most important part of the analysis, to check the model. Okay. You have a few tools you can use. The first thing is a common. This is just a statistics, part of the statistic. First, you have to determine what is your confidence level, or we call it as significance level. So some people call it as confidence level, some people call it as significance level. So please, in your Viva, if the examiner asks you what is your confidence level for the study, you should know what is your confidence level. Okay. So normally in the software, the confidence level is 95%. Yeah, 95%. But if you have a very sensitive data, which is or very sensitive response, even 0.01 or 0.1, even 0.001. So in our area, in my area, for those who involved with DNA, the molecular level, or maybe in other area also you have that kind of study. So even a small, very small numbers of differences between the response affect a lot to the process. So you can choose your confidence level at 99%, which is you only allow 1% error. This is from the F-test. I think you still remember your statistic lesson, maybe a few years back. And normally, but the common practice is it's already set in the software. Your confidence level would be 5%. So we allow the error 5% error, and our p-value must be less than 0.05. This is a common practice. Okay. Then another, the first one is the p-value less than 0.05. And then the second term, you can check whether your model is valid or not by using the R-squared. R-squared, the confidence coefficient of determination, R-squared. If you plot any graph also, you have to get the values of R-squared. So we want to have higher R-squared. So in RSM, in order for you to publish in high reputable journal or to get confidence during your Viva, of course, you want to get as much as higher R-squared. So normally, I think we will satisfy for 90% and above. Yeah, 90% and above R-squared. If you get lower than 85%, I think you should repeat. You should repeat and check what's problem with your runs. Maybe you have problem during the selection of the range. Maybe there is some error during few runs. You don't have to repeat. If you have 30 runs, maybe you don't have to repeat all the 30 runs. You choose the one with higher residual, higher error between the predicted and actual values, and then you can run that, and you can get maybe you can increase the values of the R-squared. So there is no specific values, but to be comfortable, I think if you have if you can get more than 95%, it will be the best. But if it is not possible, 90% also good, but 80 something is not really, it's not a good impression, especially when you want to publish your findings. But if you have, for example, you have five responses. Yeah, you have 5 responses. You with 5 responses, you will have 5 different equations. Okay, you have 5 different equations. So from these equations, you will have 5 different R squared. So maybe in your study, 2 or 3 responses are the most important. So that one you already get 90, another one 94, another one 99% of the R squared, and another 2 is not extremely important to the study, but you need to get the values to do the analysis. And that one you probably you get 85%, another one maybe 81%. That could be possible. I think that one is okay. It depends actually. Which area are you in? What are the factors? What are the responses? We cannot put it as 90% is the best or 95% is the best. It depends on the situation and your problems. Okay. And one more thing, how this R squared will be calculated? Of course, it will be you will get directly from the software, but you should know. You should know because this is statistic. You should know. So the values will represent. If you have the straight line would be the predicted values or the model. Okay, the model. The model is the straight line from your experimental data. So you have the dots. You have the dots around your straight line, and the variation between the dots with the straight line, which is your model, you can see the residual, the error between the experimental data and your predicted values. And from that, you can see if your dots, the experimental values, very close to the actual values, yeah, or the predicted values, then you will get higher R squared. So in order to increase the R squared values, for example, you have three factors. You have 3 factors and you have produced a polynomial equation, quadratic equation. Okay, and you from the experiment, one of the model term, which is you have x1, x2, x3. For example, x3, the single factor for x3 is insignificant, highly insignificant. Maybe the p-value, the values of the probability is around 1. We want less than 0.05 because of the 95% confidence level, but you get 1. It's extremely insignificant. But because of the factor somehow significant in the interaction effect between x3 and x1, highly significant effect, then you have to include that term, that model term, where even it is not significant, into your model equation, then your R squared will be higher because because you include that term. Because actually, when it is not significant, you don't want it to be part of your model. You can remove it, and from your model equation, you cannot see the term in your equation, and you exclude from the beginning. But somehow you need it, especially for the single term. Okay, and by adding those, maybe you have also x1, x2, x2, x3 terms is not significant, but you still include in your as your model in your equation. Then by including those many terms, even if it is not significant, your R squared will be increased. But it depends. It depends. But in general, we can say it will increase if you add so many terms. However, there is another checking instrument. We call it as adjusted R squared. So this adjusted R squared is the measurement of the variation around the dependent variables with the model. So if you include so many terms, insignificant terms, into your equation, your R adjusted R squared will be reduced. For example, you can say that, okay, I finished my experiment, I finished my ANOVA, and I got R squared 90%. But because of you include so many insignificant terms into your model, and you can say that you found that your adjusted R squared will become 60, 78, for example. So it's not synchronized. So we can see there's something wrong in your design. Okay, it is not just putting all the values or the information in your thesis, in your journal without knowing the meaning behind those informations or those statistical analysis that you have done. Okay, this is another analysis you can check, which is the residual analysis. I think I've explained just now. When you have the predicted values, the predicted values or the predicted response, that one from the for the model, okay, for the model, so the predicted values, and you have the experimental data, so it will become the experimental values or the observed values, and the differences between these observed values or the experimental values with the predicted values from the software, the error between them will be the residual. So I would like to share with you the trick. Okay, when you finish your experiment and you put everything into your software, and then you get your R squared is not good. For example, it's not good. It's not mean that if it is not good, your R squared is 50%, your R squared is 60%. It's too low. We can't do much if your R squared is too low. But if your R squared somehow 80%, 84%, you think that it's not good enough to present it in your thesis or to send for a good papers. So there is a trick that you can check your residual analysis. You have 30 runs, for example. So from the 30 runs, you check the residual analysis. Which runs give you the highest error? For example, there are 5 runs. The residual analysis is the highest. The 5 runs analysis was the highest. You run the experiment again. You rerun the experiments, the trials, only that trial. You get that 5 runs, you repeat the experiments and put the new values, and I can say that inshallah, if you manage to get the good result that nearly to the predicted value, and your R squared will be increased. Yeah, that's from my experience. That I always advise my students to do that and to see. Sometimes we don't want to repeat everything. We have spent few months, and we have to do all that we can to increase the values, to increase to validate the study. That's why we need this statistic, because we want to validate the study. And these tools I've been talking just now is about how to validate your model. And the last one is lack of fit. And this is one of the term you can find in the in your ANOVA after you finish your experiment, you finish your analysis. So lack of fit is like there is some calculation. Of course, you don't want to do it by yourself. So the software will calculate it for you, and the values will be come out in p-value. For the p-value, it will be decided whether it is significant or not. So of course, only for this lack of fit, we want it to be insignificant. We want the p-value to be more than 0.05 for 95% confidence level. We want the p-value more than 0.05 because we want the value will be insignificant. This is the only one we want to be insignificant. But the other terms in other model, we want to be significant because it will make our life easier when we want to discuss, to do discussion. We want to get a very good contour plot. We want to very good 3D response surface to discuss our result. Okay. So these are examples for the ANOVA table. Okay, you can see here. So this is the model. So this is the software will calculate it for you. This is a model. This is a degree of freedom, the sum of squares, mean square. So this is the F value from your confidence level. In this case, the confidence level is 95%. And this is the P value, probability value. So we want to get the value less than 0.05. And you can see here the model is significant. This is the first indicator, the first thing you want to check when we put all the responses in the software. We finish everything, we finish our experiment. This is the thing that we want to see after we put all the values of responses. So if you got this significant, then at least you can feel that you can relax for a while, because at least your model is significant. And maybe the thing that you need to do later on will be less inshallah will be smoother, because you get this significant model. And in this case, you have in this particular paper, this student have 3 factors. Okay, so you can see here the p value. This is 0.001, so this is significant. So the second factor also significant. The third factor, from the statistic view, is not significant. Even it's really close, yeah. It's really close to the significant term 0.05, but to do when you want to do the discussion in your thesis, it will be insignificant. Okay, but the model can be included in the equation. It depends, but I haven't shown you this the model here. This is only example for the ANOVA table. So you can see here the quadratic effects, the quadratic terms also significant, and but the interaction effect here, one is not significant. So the other one, S1, S3 is significant. This one not. This is significant, and also this one significant. So this is lack of fit. Probably the student haven't put the values. I'm not sure what is the values here, but the lack of fit should be insignificant. So you will have a problem when you want to explain if the lack of fit is significant. We want to have the model to be fit. Yeah, to be fit. That's why when lack of fit must be insignificant here. Okay, this is another example. So this is actually my first journal paper during my master study. This paper has been published in the year 2004. Yeah, year 2004, and this is a very simple ANOVA table I put in the journal. And you can see here the R squared is 94%, 95%. And also I have another table. Yeah, for this particular paper, I put another table because I have 5 factors. I don't want to present all the ANOVA full factors in one table. I make a separate table for the model terms. Okay. That's all about this is about how you want to validate your response, your result. I think this is almost done. The things that you should know as the introduction is the design resolution. I'm not sure where I have to put this, but you need to really understand the factorial design first, 2-level factorial design first, in order to understand the design resolution. When you have decided to use fractional factorial design, okay, for the fractional factorial design, there are three resolutions. Just now, I mentioned to you that fractional factorial design. For example, you have 5 factors and 2 power of 5. Instead of 32 runs, you can choose to use fractional factorial design. For example, 2 power of 5 minus 1, you will have only 60 runs. So is it enough for your study? Is it enough to discuss, to defend your study, for example? So you can discuss it based on design resolution. You can convince your panel. So for example, during my, this is one of my experience during one of my PhD student. She has been graduated last year. Okay, during her study, she actually she has decided to do two level of processes. The first one is the screening process, and the second one is the optimization using CCD, Central Composite Design, under RSM. So for the screening process, she decided to use two-level factorial design, fractional factorial design, two-level fractional factorial design, because she has 9 factors. Okay, she has 9 factors. So after 6 months, because we are dealing with enzyme demobilization process, it's not easy to get the result. It's a long way to get the result. And after few months, I think a few months, after so many times repetition, replication, and so many things, when she showed to me a result from the screening process, the response is actually the value, the yield, she got 99%. Okay, she got the values for the yield is 99% after she completed the study. And I asked her, after screening process, you obtain 99% of the yield. So what do you expect when you want to run optimization process? If you can go up to 200%, 300%. No, right? No, right. So we keep discussing, and at the end we decided that your screening process would be your optimization process. You have to stop there. You have to stop there. You don't have to do your optimization process using CCD or Box-Behnken or whatever design. You have to stop up to your fractional factorial design. But the problem is it enough? Is it enough to present the optimization only by using fractional factorial design? Definitely, if you get the right examiners really understand the process, you will be toast. Okay, you'll be toast. And that's happened in her Viva. But from the beginning, I advise her, okay, your optimization is actually your screening process, and you have done the study, you have done so many things using two-level fractional factorial design. You have to find references, you have to find any other facts that you can to defend that this study, this design enough to present as optimization process. And she did that. She did that at least she can prove the design is actually resolution 4. So that's why I want to relate this situation to the design resolution. Okay? Because you cannot proceed. You got 99% yield and your limit is 100%. You cannot extract, because when you do extraction, for example, you have something and the limitation of that, for example, you have fruit, you want to extract something from the fruit, and the amount of the material that you want to extract is 30, for example, 30 gram. And from the screening process, you already obtain 29 gram. So are you going to proceed for the optimization process? Absolutely no. You have to think while you're doing anything you do in your study. You have to think. You have to ask who, why. You have to ask why, and how. Ask why so many times. Why you have to do this? Why you choose this? Why the result like this. And in her case, 99% is the maximum. You cannot go further than that. Okay. When you do optimization, you have to prove that optimization is to optimize something. So if you got the similar result from the screening and the optimization, definitely if you submit your thesis or you submit your paper, definitely it will be rejected. What is the purpose? You are not the robot. You're doing without thinking. So that's why you have to think. Okay. So when you do this, in this case, she prepared. When I told her to prepare, she prepared all the reason that what she did actually can be considered as resolution 4. So at least when the design is in the resolution 4, then it could be accepted as optimization process. And she survived during the Viva because the examiner is the expert in this area. If you're lucky, you get the examiner is not expert in the RSM, so it's better for you, but we don't know who will be our examiners, right? So we go back to the resolution. The resolution 3, when you choose resolution 3, you can see which resolution later on. If we have time, I'm going to show you the software a little bit, and I can show to you where is resolution. Where is resolution 3, where is resolution 4, and where is resolution 5 in fractional factorial design. So when you choose resolution 3 design, anything that you get from the analysis, the model, okay, the model that has been obtained from the study, the main effect is the single factor. Okay, the main effect will be confounded with two factors interactions. Okay, even though during your experiment you choose 2 power of 4, yeah, you choose to do 2 power of 4, which is 16 runs, instead of full factorial design 2 power of 5, which are 32 runs. So you cut half of your experimental trial, but you still can get you can discuss, observe, and see the behavior of the factors, which is the main effects confounded with two-factor interactions, at least. Okay, at least. This is the meanings of resolution 3. So it is potential for large numbers of factors in the experiment. So normally we can use it for screening experiment. If other people ask you why you choose what is happening inside the process, because you cut half of your experiment, you should do 32, but you do only you want to do 16 runs only. So because of I choose to use resolution 3, and whatever I get from the study, my main effects were confounded with two-factor interactions. I think it's enough for my screening process. That's why I choose this resolution 3, and towards the end, I'm going to do optimization after I eliminate insignificant factors. This is a normal reason that you can use for your screening process. And how about resolution 4? The resolution 4, if you have main factors confounded with 4-factor interactions and the 2 factors confounded with 3 factors interactions. So if you have more than 4 factors, normally when we do screening, we have large number of factors. I already show you 8, 10 numbers of factors. So if we choose a very low number of experiment, we can say that we can only cater for the main interaction, main factors or single effects. How about the other factors, which is the main interaction, which are the 2-factor interaction, 3-factor interaction, 4-factor interaction side. But by using resolution 4 design, you can have this informations. So you only need to evaluate the main effects and also 2-factor interaction without check the effect of 4-factor and 3-factor interactions. Okay, and the best is the resolution 5, because in resolution 5 You can have main factor confounded with 4 factor and 2 factor confounded with 3 factor interaction. Okay. These are about resolution. It is okay if you don't really understand, or if you are really in the very beginning of the study of this RSM or DOE or factorial design, you will be confusing. It's normal. And if you after the course, if you still need sometimes to do adjustment, or maybe you still have to do the planning, and you will start your experiment maybe after a year, definitely you will forget everything. You need to practice. Yeah? You need to practice. At least you need to get journals from the areas, and you can start seeing how people write the levels, write the analysis, the ANOVA, the equation, at least. Yeah, try to get the good journals. So before we stop, I would like to share with you. I think I already shared with you throughout the previous from the beginning. I already indirectly shared with you how we want to design our work, our experiment. So if I want to start from zero, how do I start? Okay. First, of course, I have to do literature review. I know the process. I know what I want to do, and I need to determine what are those variables involved. I have to go back to find related journals in the area. Of course, so many things. In the very beginning, you don't know which one is suitable for you, and first you have to get all those information. Prepare a table suitable for specifically for your study, and then start to think about screening process. If you have many factors, then start to think about screening process. So in order to do screening process, you still can remember from the beginning I mentioned that you can do whether literature review screening process or half factors from the literature, you screen through the literature, or you can do preliminary study. Because some factors you don't know, what are those range you want to use? Yeah, you can do preliminary study. Okay, from the preliminary study, somehow, for example, if you're dealing with microorganism, for example, bacteria. Some bacteria, we have thermophilic bacteria. For thermophilic bacteria, the normal condition bacteria will die, or will die at maybe after 37. From 30 to 37, it's only the limitation for our study for the temperature. But for the thermophilic bacteria, maybe we can go up to 70 to 60. So we don't know. We want to stop at what temperature to get the range for our study. It is only for screening. Not yet. We are not talking about the optimization part. Only for the screening. So you can do preliminary study. You can conduct a preliminary study from 30, 35, 40, 45, 15, and then you can have your graph, and then you can make a decision from that result. What is your range for that study to be incorporated into your screening process? And later on, when you have those factors for your screening process, maybe 5 factors, maybe 10 factors, and then you also already decided those ranges for that specific or for that particular factors, then you can start your screening process. And when you want to start your screening process, another question will come up. What is the best method for my screening process? Am I going to use OFAC, one factor at a time, or the conventional method? Or am I going to use factorial design, two-level factorial design? How about the Plackett-Berman design? How about the Taguchi method? So this design that I put it here, all you can choose for your screening process. And why we call it a screening process, and why this design excluded the OFAC? The other design you can get linear, regression analysis. You can get linear equation because it is for screening process. Okay, and from my experience, I always advise my student when you have categorical factors, categorical factors such as type of microbe. You have 3 types of fungus, for example. So are you going to do factorial design? No, definitely no. I will ask them to do for categorical factor. Because if you have categorical factor, you combined with numerical factor, you put in the factorial design, you will have, I can say that you have double, triple numbers of runs. It will be very long list of runs you need to conduct. So if you have categorical factor, my advice is go for OFAC. For example, in our study, we have to study the when we do medium optimization for the microorganism, we have to determine which the type of carbon source. For example, we have so many carbon source to choose: glucose, sucrose, fructose, for example, starch. So we have 4 types of carbon sources. So which one is the best? We want to do optimization. So I always advise them to just go for OFAC first. Decide it first. Yeah. Then you can do the numerical screening or numerical optimization later when you finish your categorical factor. Unless it is you have decided, you have arranged everything properly, you have organized properly, then you can include at least 1 or 2 categorical factors in your RSM or in your factorial design. Can, but you have to organize it properly. And then after you finish your screening process, the objective of the screening process is more on the to get or to determine the significant or insignificant factors. When you get the significant factors, for example, from the 8 runs, from the 8 factors, only 4 is significant, and these 4 will be used for the next level, which is optimization process. So I'm sorry, because this 2 hours is definitely not enough to cover everything. So many things actually I want to share with you, but I couldn't fit it into this very limited time. So the next process is optimization. Actually, optimization process is similar to the 2-level factorial design. Only the equation will be polynomial equation, and also the type of design, of course, definitely will be different from the previous one. So you can use CCD, Central Composite Design. It's a famous design, I think. CCD. Actually, CCD is part of factorial design. Central Composite Design is factorial design, but with because it's not only 2 factors, two level. In CCD, we have five levels. You have to add the, what we call it, the positive alpha and the negative alpha, what we call it in the normal term, I can't recall just now. But instead of we have -1 and +1, low and high, you have also to put the values which is negative alpha and positive alpha, which is beyond that low and high value that you have decided in the first place. So instead of 2 level plus the center point 3 levels, so you will have another 2 levels, 2 points, which is totally you have 5 points. And definitely when you have these 5 points, you can get the good curvature if you have the curvature, the optimum point in your response surface later. So that's why CCD is part of optimization process, or the higher order model equation will be produced by using CCD. It's part of factorial design. The concept is similar to factorial design because it is 2-level factorial design. And also next is Box-Bangkit. Box-Bangkit also one of the familiar designs that have been chosen in many optimization process. It has 3 levels. If in 2-level factorial design we have -1 and +1, but in Box-Bangkit we have to put exactly the values of 0, the center point. in two-level factorial design, we have the choice whether we want to just to do the center point as part of the experiment to see the error, pure error. But in Box-Bacon, the zero, the center point is a must. It's part of the run. It's part of the run. The zero, -1, and +1. So it's actually 3-level. Instead of 2-level, it's actually 3 levels. And the 3-level factorial design similar, almost similar to Box-Bacon, which is we have 3 levels. So maybe in the latest software, the version 13, I'm not sure how it looks like. Maybe there are some other designs has been included and some has been excluded from the software. I'm not sure because I'm still fixed with the very old version 20 years ago. Okay, I think it's already 11. I think I'm going to stop there. I also share some of the, this is just to show you what is response surface. Actually, the 3D surface you can produce from the software, and this is actually what we want. When we want to get the optimum point. We want to get the optimum point, so we want to have this kind of very nice curve, very nice curvature in our at the end of our analysis. Okay, so how to get this? There is a tips. If you conduct a very good screening process, especially if you do OFAC. I can see this is from my experience. If you do OFAC, because you have each of the factors, you have the graph. Okay, you have the graph. So when you do OFAC, you have a very clear picture the range for your optimization study. For example, for the temperature, for the screening process, you have a temperature 10 to 100, for example, 10, 20, 30, up to 100. And from the screening, you can see that 50, 60, 70, 60 is the optimum. 60 is the highest yield. You obtain highest yield at 60 degrees Celsius, and for the optimization, you choose 50 to 70 as your range. That is the purpose of screening. Actually, the screening is to get the proper range for your optimization study. So for example, in this study, 60 is the highest, but we don't consider the interaction. We only check for the single factor because it is OFAC. So for the optimization study, for example, you want to use CCD, you put the temperature as one of the factor, and the range you put 50, 70. You put 2 level, 50 and 70, and you run the experiment plus the other factors. For example, other factors also you do the same thing. Okay, and at the end, if all the values from the screening process is the best range, which at the end will contribute to the optimum point, then only you can get a very nice curvature, very nice maximum response. This kind of curve, it's not very nice. The one which is very nice, you can get a very nice contour in the center. So that's why screening, the determination of range is extremely important. If not, you will get this saddle point. This is the optimum point at the end of this. But why at the end we'll get this saddle point? Because of the range. If I'm the one who already familiar with this area for almost 20 years, and I see saddle point, straight away I can tell you that, okay, this is because of the range. Yeah, because of range you will get saddle point. Sometimes for me, I don't want to blame anything. I don't want to blame to blame the student because maybe the screening process is not right, for example. It's not because of that. If the student really understand what is happening towards her process or his process is okay, maybe the student already did everything. The temperature, for example, the highest temperature for the study is 100. You cannot go more than 100 because of the limitation of the equipment, for example, because of the limitation of the cost. You cannot go for 100. But the process you got is 100. The 100 is the maximum. And the student put the optimization point for the range 50 to 100. Definitely you will get saddle point because the highest from the screening definitely shows the optimum is at 100. But why you put 50 to 100? Maybe in the first place, you can exclude that factor and fix the value at 100 as the background factors. Or if you think that the factor would be beneficial to see the interaction effects, you want to see the interaction effect because it's even if it is at 100, but it's still okay, it's still good at maybe 80, and it will be produce high value when it will be interacted with the other factors. For example, you know what is happening, then you put that. Definitely you won't get that optimum point contour plot. Yeah. Okay, I think that's all from the slides that I want to share with you. We still have some time. I would like to show to you okay, maybe I would like to ask the chairman whether I should proceed with the software. Maybe I just want to show the software how it looks like, or maybe we can go to the question and answer. So up to the chairman. I think I finished my slides.
I think you can show. I think Prof, we can show the software first before we proceed to the Q&A session.
Okay. Actually, I'm not sure why my software is become like this, because I have the Design Expert 6 for a long time ago, and I just remember that in 2018 I bought this Design Expert 10 with 2 license. Under academic license, we can get the cost around 1,200, and I share it with my student. And just recently, I asked one of my friend to give me the link for the version for this Design Expert 10 version, and suddenly everything changed into this Design Expert 10. So, okay. The look of the software is quite different from the previous one. So just I want to show you some of the things that I mentioned in my slides just now. So you can see here, this is, you can see this you can see the software, right? Adrian, you can see the software? You think
Can.
Can. Okay. So from here, you can see that we have factorial here, the factorial and response surface. So for factorial, normally this is for screening process. For screening process, this is a normal so many sebenarnya, so many design you can choose, but the basic is still the same. You can choose 2-level factorial design here, and also you can have Blackett Berman here, you can have Taguchi here, but the thing that I want to show you is the 2-level factorial design, because it's the most common design, and also you can see the resolution. Okay, if you have 2 factors here, 2 factors is too low. For example, we have 5 factors. So if we have 5 factors here, if you want to conduct a full factorial design, you need to do 32 runs. You can see here, 32 runs for 2-level factorial design for 5 factors. If you want to choose resolution 3 here, you can choose resolution 3, 5 minus 2, and you only need to run for 8 runs only. Okay, you can see here, from full factorial design, 32 runs, you can reduce tremendously of your number of experiments to 8 runs only. It's okay. If your objective is just to use to get the significant to do the screening and to get the significant factors, and only for and only resolution 3 is enough for your study. It is just screening, it's not optimization process, for example. Okay, for example, if you have 10 numbers of factors, so you can choose resolution 4. You can only need to run 32 runs, for example. So whatever you choose, you need to know. You have to justify, of course. You have to justify why, and you need to know the concept behind it. And I think that's all. As long as you can justify, you have the references, I think it's okay. And you can do replication here. You can see here is replicates. If you want to replicate, you can put how many times you want to replicate the whole experiment. This is center point. If you want to add center point, the 0 points, you can add how many times you want to do the replication of your center point. And that's all. And you can continue. For example, I have 3 factors. I want to do 3 full factors, no replication. I want to have a two center points. So I continue. Okay. So it will come like this. So this is you can put your pH, for example, temperature, and also time. Or you can put x1, x2, or x3 type. This is the I mentioned whether it is numerical or categorical. Numerical for numbers, categorical for type of qualitative. So this is low and high. You can just put it as coded. We call it as coded factors here, or you can put actual. Yeah, if you put coded, let it be coded here, but only you know what is the low for pH, right? For example, 4 to 10, for example, temperature 10 to 100, time 1 hour to 10 hours, for example. So this is the unit. You have to put the unit here, and you have 2 responses, for example. So you can put response 1, what is activity? For example, response 1 is yield. Response 2 is biomass, for example. And you put the unit here. Continue. Finish. And this is the thing that I mentioned to you. It will come up from the software. You make it as a... Okay, you can put here. You can see here, this is the standard order. So from the standard order, you can see the factors here, 1, 1, 1, 1, 10, 10. So why I keep saying that you have to do randomization, because from the software, normally it will give you in the proper run. So you can see here all the time, run number up to run number 4 also still have the 1. So you have the low values here. Okay, and this is the highest values. This is the center point. I want to repeat 2 times of the center point, the 0. So you can see here that if you do randomization, next to the standard is the run. So you can do run number 4, standard number 4 as your run number 1. Then you do this one, number 2, and you do number 3. Then you randomize your experiment. You also can change the values here into the coded to see it clearly. Sometimes you don't want to see in actual values, and you can put here in coded values. Okay, for example, you have yield here. I just put values, any values. Just we don't have the right values. The yield here. This is you have to go to your to the lab and do your experiment. When you get this, and then you go to the lab, and after you finish all these 10 runs, and you come back and you put all the values here, then you can do the analysis. So the yield. So the analysis, this is effects, because this is screening or factorial. So factorial design, you have to choose the effects. You have to choose the effect. It's already, I think you have to choose. Kalau if you're using Statistica, maybe you can see it from the Pareto chart. You can check the effects. Okay, this is negative effect and also the positive effect. So you have to read what does it mean by negative effect and positive effect, and you can go to the ANOVA. Oh, the software asks you to choose everything. Sometimes it needs but I don't want. I'm not sure because I just put the value, so cannot. Okay, you can see here, this is ANOVA. So this is the software looks like, but you have to get you have to extract all the information and put into a proper nice table, and you can do whatever you want. You can do design whatever you want, whatever you want to put in your thesis or in your paper later. So you can see here the model is significant, even though I just put a random data. So the model here is significant. Of course, it is a linear equation. I don't need to check whether it is quadratic or cubic or whatever. It is definitely is linear because it is factorial design. And this is one of my factors, the C. The C is significant. Only C is significant here. Yeah, A and B is not significant. From the effect just now, we can see the things below the line is significant, above the line is not significant. Okay, AB, BC is a two-factor interaction. You can see it is significant. BC also significant. ABC, three-factor interaction also significant. And the other factors which are not included from the beginning, I have excluded. I'm not sure. Only these 4. Okay, only these 4 have been included in as my model. You can see here 4. So because these are only significant terms to perform my mathematical modeling or equation. So this is the full ANOVA. You can see here lack of fit. You can see here pure error because you run the center point. It can predict pure error. There is no pure error here. And also, so this is your R squared, 96%. This is your adjusted R squared, 94%, because I only included all the significant terms. If I put all the insignificant terms, so definitely my adjusted R squared will be reduced. Okay, and this is the equation. Y equals to 59 plus 13.75. C is x3. If you want to choose ABC, if you want to choose x1, x2, x3, depends on you. You need to interpret it by yourself. And this is the equation using coded -1, +1. This is the equation using actual value, the one that you put just now. And you have this is the normal plot versus residual. This is the data, the predicted values, and the point is the experimental values. And you can have the model graph. You can see the interaction. Yeah, you can see there is interaction, very huge interaction because there is no interaction here. Let me see. So there are some interaction here. So you only the one can decide what you want to do, which one you want to highlight in your study, in your paper, in your thesis. Okay. And at the end, why I think design expert is very good, because in the optimization, we have a numerical. You can choose these three my factors, and the yield I want to have a maximum yield within the range. Okay, this is the RAM. We call it the RAM. So I want to get 100% yield, and this is the optimum values that has been reported. So this is the numerical method, the solution that have been provided by the software. But I choose the first one because the desirability is the highest, and I have to take these values. Why the value is negative? Because this is in the coded. So if I want to see in the actual, so at pH 9, at temperature 11, and at time 9 hours, I will get 100% yield with the desirability 1. And I want to choose this as my optimum point. I have to go back to the lab. I have to try to put all these values and check whether I still can get this yield. That is validation test. We call it as validation test. And then you can present your data in terms of graphs. Because this is linear equation, I think it's enough just to present based on the contour, the two contour plot. No need to display it in no need to display it in design point coded. Because this is 3D. No need to present it in 3D because it is it's a linear equation. Okay. Please choose a single response. Okay, single response. I'm sorry because I'm not very familiar with the version 10. I really, my experience only for version 6. I think the interface also quite different from the previous one. So view, okay, view 3D. I cannot see. So for the 3D, because it is linear, you can get only this kind of surface. But for me, it should be linear, but I'm not sure why we get this kind of saddle point here. Maybe because of the point that I put into randomly. But normally we can get this straight line. Yeah. So I think that's all I can show to you. Maybe I want to show to you a little bit. No. Okay. Instead of this factorial, we also have response surface here. Okay. The response surface, you can choose any design from this response surface menu for your optimization, because you can get higher order model or polynomial model, whether you want to use central composite design, same to the factorial design. You can only need to put low and high. Also, you can decide whether you want to make it as a the alpha. It depends whether you want to make it as a rotatable, orthogonal, or pre-centered. You have to learn more. This you need to read more. What does it mean by these alpha values? It depends. And the software will produce the runs, and you go and take the runs, take the trial that you should do, and go to the lab, run the experiments, and come back and put the values and do the analysis. You can also choose Box-Blanken design. Okay, this is for one factor. And also, this is central composite. And also, we also still have one, I think this is extra information that you should know, because sometimes you have conducted a very good OFAT. We have a very good OFAT. Some people, they just conduct just not very good OFAT experimental procedure. But if you have very good one, you can convert that data and result into this. You can put into this historical design, and you can come up with a very good result, and you can interpret that, and you can do analysis, and you can present with those tools that you have in this software. Okay, I think that's all, Adrian. It's already
Okay, Prof.
11:50.
Okay, Prof. So we have few questions. The first is, Doctor, how to arrange design of an experiment for RMS if we have 3 factor and 3 levels?
How to
arrange design of experiment DOE for RMS if we have 3 factors and 3 levels?
3 factors and 3 levels. Okay. What do you mean by 3 factors and 3 levels? First, you have to really understand the concept of the design that you have chosen. If you want to use 3-level factorial, we have 2-level factorial design and we have 3-level factorial designs. For 2-level factorial design, I hope that you really understand that you only need to put the value of 2 levels, the lower and the higher. Yeah, the low and high value, -1 and +1. And the 0, the center point, will be produced when you ask that. When you ask the software to add that as part of your run. It's only for validation if there is a curvature or for pure error. And if you want to run 3-level factorial design, is actually under the surface, the response surface. 3-level, we have 3-level factorial design, but I'm not sure in this new design, this 10, we have or not. We have or not the 3-level, but at that time, by using Design Expert 6, yes, we have 3-level. The 3 levels is you put the low and high. We are talking about 3-level factorial design, but if you want to use Box-Bangtan design, also 3-level. Okay, that's why I think I say it depends on the design that you want to use and the purpose of the experiment, whether you want to do optimization or screening. For screening, you don't have to use 3-level because it's optimization. It's a response surface. If you want to do optimization by using 3-level, you can choose 3-level factorial design method or Box-Bangtan method. So you have to put the value of low, -1, and also +1. And the software will detect the 0, the center point, and the center point also will be incorporated into your trial. Not only if you still remember the thing that I have shown you just now, I only put -1 and 1, and if I exclude the center point, the 0, you only need to run all the experiment with -1 and 1. But for 3-level, you have to run all the experiment including the 0. So the number of experiment definitely will be increased. It's not similar to 2-level. Okay, I hope that you can and how to calculate the number of experiment is 3 power of 3. If you're using 2-level, 2 power of 3, but for 3-level, the number of experiment will become 3 power of 3. So what is 3 power of 3? So you calculate by yourself. So the number will be increased compared to the 2-level factorial design. That's all. Yeah, Adrian, I hope I answered that question.
Okay, there's a few more, Doctor. Doctor, can we screen the factor based on the literature review only without doing the factorial design, and straight away doing CCD?
Possible. I think I
Possible.
mentioned this now. Yeah, it's possible. If you can, if you have a very established method, you use all established raw material, and maybe you just want to do a few preliminary study. For example, you have 4 factors, and you think that these 4 factors from your literature review, 4 factors is definitely extremely significant to the study in all the literature review you have searched, and but maybe the material is quite different from others, and you just need to run that material. For example, I'm not sure what kind of material. For example, you just want to run one preliminary study just to determine the range for that particular 1 factor, and then you just use all the factors that you have been decided from the literature review plus the range. The problem is the range actually. So for the range, of course, we can run preliminary study before we straight away to the optimization, before we proceed with the optimization process without doing screening. And the screening process have been done using literature review and some preliminary study. It's possible.
Okay, there's one more. Hi, Doctor. I can't remember the situation, but there was one time when the randomization suggests negative value for my experiment. So what do we do if the randomization suggests negative value for experiment when our variables are numerical variables such as concentration or weight?
What is the question? I can't get it.
Okay. When the student done the randomization suggests the randomization suggests negative value for her experiment.
Negative
Uh,
value?
uh,
How come randomization suggests negative value? Randomization is a principle of the study. I'm not sure is that the correct question, because randomization, if you have 10 runs, you randomize, not you run the experiment number 10 first, number 5 second, number 3 third, number 3 run, number 3 maybe the third run number 7 the 4th run. That is randomization. Or the question is about CCD. Can the person ask the question?
The person has question. Can you on your mic?
Maybe the person asked the question.
One, panggilan 1, panggilan 2, panggilan 3. Okay, we proceed to the next question. Can the RSM used for monitoring, Doctor? Can the RSM used for monitoring?
Monitoring? Is monitoring for what? The question is too general. I don't want to do assumption to answer that question. Maybe you can specify the question.
Okay, the person who asking this question, please come. 1, panggilan 1, panggilan 2, panggilan 3. Okay, we proceed to the next question. Doctor, when using the RSM CCD, what's the differences for the alpha option? Meaning, what are the differences between alpha, rotatable, spherical, orthogonal, quadratic, practical, and fact-centered? 2, how do we want to know which alpha option are the best for the experiment?
It's actually technical thing. You have to read and you need to match what you need. What I can say, in the first place, I don't care actually whether it's orthogonal or face-centered or rotatable. It's just a part of the technical things that you have to decide in the software. But the most important thing is your design, your range. Because when you have decided to use CCD, instead of choosing the right range for -1 and +1, you have to make sure that the alpha value will be able to perform during the experiment. For example, some students, they like, for example, when you want to study the concentration, concentration, for example, concentration of acid, but one of the factor, and they want to study whether it's a zero concentration, without any additional of the acid to that process, and up to 10%, for example. For the CCD, so the student put the value -1, 0, and the value for +1, 1, 10. And the student decided to use CCD. What happened to the process? When you put the values, the software will suggest your whatever the alpha that they have chosen, whether face-centered or orthogonal or rotatable, and the alpha would be for face-centered, of course, it will add 1. For example, 1 is a face-centered. The values of alpha will be similar to the if you put in terms of figure, the values will still how I want to explain this, because we have to show with the okay. For example, percentage is 1. Okay. Oh, there is no figure, because in the previous one we can see the how it looks like. The values will be 1. It will be at 1. So for positive alpha, the value from my example will become 11. For example, 11. That is a calculation, will be calculated by the software. Don't worry about that. But if you choose face-centered, the value will be quite near to the value, the range that you put. For example, you put the acid concentration just now 10, and the alpha will become 11, positive alpha, and the negative alpha from 0 will become -1. So when you want to conduct your experiment, how about that experiment? Can you do the concentration at the level of -1? It's impossible. That's why still whatever it is, the choice for your range is the most important, extremely important. For example, for the microbe study, the microbe will die at 30. For example, will not active at 30, but still okay. And you choose your temperature to be studied from 30 to 40 for the microbe, for the biomass, for example. You want to see the microbe, the behavior of the microbe or bacteria. And you want to run CCD. And you choose rotatable. Rotatable is 1.4. And the software will calculate the amount. From 30, it will suggest 27.6, for example. 27.6 for negative alpha, and maybe 43.4 for positive alpha. Okay, then of course you can do that experiment, but you will get 0 yield because the bacteria will die eventually at that temperature. So again, even though you want to use CCD, you know, the most important thing is not this rotatable, spherical, orthogonal. It depends how far you want to move from your low and high value just now that you have decided. How far you want to move for the negative and positive alpha depends on the choices that you have here. But at the end, the values that have been chosen, is it possible to run the experiment? Is the most important. That's all what I can answer.
Okay, Prof. We have one more from Nizam Razak. He asked about 4 questions. The first one is, if screening is a must, can we use the parameter in the RSM?
What is the question? Is screening is
a must? Can we use the parameters in the RSM? Can we just use the parameters in the RSM
without screening?
He asked that is screening is a must.
I think the same. I think I understand that. Whatever it is, I have that kind of experience, and some of my students also did that previously without screening. But even though you mentioned that you haven't done any screening, but you actually done it in your literature review, because the process to choose the factors, to choose the range, is actually the screening process. Maybe you are not doing, you are planning not to do it experimental experiments, but you just want to depends on the literature review. So it's actually a screening process. Okay. Then you can straight away to do RSM or optimization process, no problem.
Okay, the second question from the same person regarding the p-value. From what I read throughout the paper, it must be below 0.005 and more than 0.005. The model is not significant. How to make the model be significant?
Why is 0.05? The model is not significant. The model based on the confidence level that you have chosen. If you choose 95% confidence level, so for the p-value, you have to get the model to be less than 0.05. If you choose your confidence level 99%, so you have to make sure the models and also the model terms to be significant. The values must be less than 0.01. That is the first place that you should know. And then if you get your model is not significant, the problem probably based on the factors and also the range. The range is not correct. The range is not suitable. The factors are too many insignificant terms. So too many insignificant parameters or factors. Because you want to do optimization. Maybe you skip the screening. You don't know what is happening, even though somehow when you do screening through literature review, but it's not actually it's not actually similar when you conduct by yourself, because some of the materials different from the literature review. But you straight away run your experiment from the factors selection from the literature review, and factors, I'm not afraid. Factors is somehow is similar. Not I don't have any problem with factor selection, but the problem is with the range selection. When students have difficulties in the model, when their model is not significant, their R-squared is far from 90%, the main problem is actually the range. The range, the selection of the range. So the problem is actually the range. I guess because the question is also general, so that's the only I can answer generally.
Okay. Okay, one more. Prof, from what I have read, there's a few methods of RSM with two factorial design, BBD, CCD, Taguchi, and more. Among them, Taguchi is the best. Can you explain Taguchi briefly?
I haven't used Taguchi. Box-Benken also I haven't used, but my students, some of my students use Box-Benken, but I haven't used Taguchi, and also but the most common is CCD. Most of my students use CCD. So I like CCD because the concept is from two-level factorial design. It's two-level factorial design actually. It's only we add the alpha, the alpha, and it will become RSM, because of the from the two we have 5 points. For Box-Benken, it's similar to three-level factorial design. Yeah, the one that I answered from the beginning to three-level factorial design. You have to put three points. These 3 points will be incorporated into your run. But for CCD, no, only 2. -1, 1. That's only the range, the things that you need to run. For alpha, also only a few runs, not many. So your numbers of run will be reduced. Box-Benken, probably number of run will be reduced, but it's the concept is quite different, because Box-Benken based on three-level factorial design. And three-level factorial design is similar to Box-Benken, almost similar. And Taguchi, I think Taguchi is not fall under RSM. It's actually under factorial design. You only can get linear equation. Normally Taguchi, Plackett-Berman, and two-level factorial design, regular two-level factorial design is only for screening because you only can produce linear equation, not polynomial. Okay.
Okay. And we have, dear doctor, how to avoid set the point when you're using the CCD is the type of response, no specific optimum value, plays an important role while determining the shape of the produced 3D graph.
Differences for alpha options.
No. How to avoid the set the point when using the CCD is the type of the response, no specific optimum value, plays an important role while determining the shape of the produced 3D graph.
I can't really get the question. Why, correct me if I'm wrong. Why, what is the question again? Why is the?
Is the type of response plays an important role while determining the shape of the produced 3D graph.
Okay. The type of responses, whatever you obtain at the end of your design, after you finish your statistical analysis, you get the ANOVA and also your plot. It's actually based on what is the input for your study. So you have to blend everything to the factors and also to the range. That's all. That's all I can answer. You cannot respond also is play important role, but respond is somehow you need to do the analysis maybe based on your study because you want to get the optimum point of something. Because you want to get the highest yield of the biomass, for instance, you want to increase the biomass. The objective of your study is to optimize the biomass. So the response is fixed. Maybe some other response you add in. But the main things is what is the factors, what are those factors you want to add, and what are the ranges involved to the factors is the most important thing that could design the or that contributed what is happening to the output variables, because response is dependent variables. It's dependent variables. It depends on the input, the factors that you put the values. Okay, Adrian?
Okay, and then we have the last question. I think the last question for this session. Salam, doctor, for confirmation test after RSM, is it enough for only 6 testing? Is the selection of confirmation test coming from the CCD table?
Confirmation test or validation test. I'm not sure if I can answer it. I understand the question correctly, but what I think the confirmation test is maybe you mean it by validation test. Maybe when you run your when you finish your optimization process, and you will come, the software will suggest you with the number of runs that possible as the optimum points for your study, and you take the values and go to the lab. Normally, I would suggest my student to run at least three times, to run the similar process, the similar factors values to check whether the analysis will be similar to the suggested from the model. So maybe we can accept around 5% error. If the yield from the optimum optimization process, you get 100, for example, you get 100 gram, 100 gram. You can go to up 100 gram by using those factors that has been optimized from the process. And you go to the lab, use all those optimized factors that has been suggested. And from the validation test at the lab, maybe you get the first run you get 19.8, the second run you get 105, and then you get another run, you get 101, and then maybe you can average the values, whatever it is, and then you can check with the proposed or the predicted values from the software. So as long as it is within 5%, it depends on the nature of the experiment. Some research maybe 5% is too big, but in our research, 5% is still okay, acceptable, because we also use 95% confidence level. We allow 5% error. So as long as these three validation tests meet 5% error compared to the predicted from the software, so that is the only validation test that we do in our study, for my case, for my student case. Okay.
Okay, thank you, Prof. Since we have limited time, we have come to the end of our online workshop today. Thank you, Associate Prof. Dr. Roshanida Abdul Rahman. It is indeed a pleasure to have honorable guests and participants for joining our workshop today. I hope the tips and tricks shared by Prof will be useful and give more motivation to all the participants to stay in the research work while constantly learning new things in the research journey. There's one more thing I would like you all to do. Please turn on your camera so that our community can capture our picture.